Hi everyone. So now we are going to start studying about CMOS power dissipation. In CMOS, we will see the power dissipation. So before that, let's see a simple RC circuit based equation so that I could know whether you know about energy or power. So you need to find the energy delivered by the voltage source and energy stored by the capacitor. Okay. So what will be the energy stored by the capacitor, that we already know. At steady state, what will be the energy stored by the capacitor? Half CV square. Right. At steady state, it will come to VDD. Right. So at steady state, it is having VDD voltage. So energy stored by the capacitor will be half C VDD square. What will be the energy supplied by the voltage source? So how I can find? EV I am calling it. That would be voltage, that is VDD, into the current that is flowing from it, into dt for a time 0 to infinity. Voltage into current into dt. Right? This is your energy. So from 0 to infinity, VDD is the constant value. What is the current expression? Initially it is VDD by R, then it will be exponentially decaying. If you solve this, what you are gonna get? VDD by, here you are gonna get VDD square by R is there, and then R square C you are gonna get here, e to the power, sorry, VDD by R and e to the power minus T by RC. 0 to infinity, there will be minus sign as well, and here there will be RC coming. So this and this will get cancelled, then you can put the values. What you are going to get here is that C VDD square. Right? So energy supplied by the voltage source will be C VDD square. So in this configuration, energy that is supplied by the voltage source is C VDD square. The capacitor that is storing the energy, that is half C VDD square. So how much energy is dissipated across the resistor? Half C VDD square, right? Across the resistor, half C VDD square is dissipated. Capacitor is storing half C VDD square and total supplied is C VDD square. So this is the conclusion. Total supplied C VDD square. Across the resistor dissipated half C VDD square and capacitor is storing half C VDD square. So this you need to know. Now we will see the power consumption in CMOS. So in CMOS, there could be total 3 type of power consumption: dynamic power, short circuit power and leakage power. So we will understand one by one what do you mean by all these powers. So basically how the power consumption will be there. Let's just say this is my CMOS circuit and at the output I am having some load. If my input is continuously changing, so my output will also will be continuously changing. Like this. For 0 it will go 1, 1, 0, 1, 0. Output will also continuously change. So in this process of continuous changing, there will be some power consumption. So that we need to find. Now let's just say, now I am finding dynamic power, but forget about this term. Just understand simple analogy here. What I am doing is that I am giving V voltage here and then I am changing to 0. From V to 0 I am changing. When it was applied V potential, when here I was having V, you can say it is 5 volt. Okay, and this is 0 volt. When there was 5 volt here, at that time this was on. If this was on, that means capacitor would have been discharged to 0. When 5 volt was there, NMOS was on, that means capacitor would have been discharged to 0. So this potential would have been 0. When this 0 is applied. Now this 0 is applied. Now if this 0 is applied, this PMOS will turn on. If this PMOS turns on, what will happen? This will be replaced with a simple resistor, which I am calling as RP. This is your VDD. And capacitor is already totally discharged. So capacitor is having CL voltage. Right? Now what will happen? From here, how much energy will go out? How much energy this VDD will provide? C VDD square. How much this capacitor will store? This capacitor will be eventually going to charge up to VDD only. This is the steady state I am writing. How much it will store? Half C VDD square. And how much is dissipated across the PMOS? How much is dissipated across the PMOS? That is half C VDD square. So what is the power dissipated across PMOS? That is, so not power, sorry, we are talking about energy only. We will come to the power. Now we are talking about energy. So C VDD square is coming from VDD voltage source. Half C VDD square is dissipated in the PMOS. Right? Now if I take the other case, if I go from 0 to V, so previously I was having 0. That means my NMOS was on. If my my PMOS was on. Previously I was having 0, so my PMOS was on. If PMOS was on, that means it would have charged it to VDD voltage already. This 0 was there for a very long time. This 0 was there for a very long time. So my PMOS was on. That means my capacitor would have charged up to VDD. Right? Now what will happen? This V will come in action. If V comes in action, then this NMOS will turn on. So if NMOS turns on, then it will be replaced with a simple resistor. So this question also we should have solved, but I hope you know it already. If this is charged to VDD, so it is having half CVDD square energy. Now what will happen to this VDD voltage? This will be completely discharged here. So eventually the energy will go towards 0. So where the energy is dissipated? Across the resistor, right? What I mean to say is that the CL is already charged to VDD. Now this will be discharged across the resistor. Complete voltage will be discharged across the resistor. From VDD to V will go to 0. It was storing an energy of half CVDD square. So how much energy is dissipated across the resistor? Half CVDD square only. You can write down the equation and find the energy. Okay, what you will write down? You will write down the equation. How you will write down the equation? You need to write down energy across the resistor R1 I am finding. So voltage and current equation you need to write down from 0 to infinity. Voltage is also going down and current is also going down. So what will be the equation of voltage? Voltage is going down exponentially from VDD to this, and current is also going down. So initially current was VDD by R, then also it is going down to 0. In that manner you can find out, and then dt. You integrate that, you find out the value, what that will come out to be? That will come out to be half CVDD square only. And intuitively also you can understand that this was storing half CVDD square. Now it is completely discharging through the resistor. So the energy that it was storing, that has been dissipated across the resistor only. So that would be half CVDD square. Right? So in a complete cycle, during charging and during discharging, total energy dissipated in CMOS. First it was charging, first output was charging in this case, and it was discharging. What do I mean by that is that for this input, completely here it is charging, output is, sorry, if you are going from 0 to 1, that means output is discharging. If you are coming from 1 to 0, that means output is charging. So here there will be discharging, in this case there will be discharging, right? You can see this is the case, 0 to 1, 0 to V volt you can say, and in this case there will be charging. So in this complete cycle, what is the total energy dissipated in CMOS? Across the PMOS it was half CVDD square, and across the NMOS it was half CVDD square. So total energy is CVDD square. Agree to this point? Now what did you see here? This half CVDD square, or you can directly say this complete CVDD square is not a function of RP and RN. This is not a function of this resistance RP, R on. Why I am writing R on? I should write Rn. On resistance of NMOS, and here this is on resistance of PMOS. So this is not a function of RP and Rn. That means it doesn't depend on design parameter. What do I mean by design parameter? Mu n, it could be mu n W by L. On all these parameters it is not depending, because your RP and Rn is depending on mu n and W by L. So it is not depending on those parameters. Now the thing is, let's just say this is your CMOS inverter, and then another CMOS inverter is there in series. So when I write this CL, what do I mean by that? From where this CL is coming? The CL is certainly coming from the input capacitance of the next stage. In the next stage as well, there is some inverter connected, or any IC is, any logic circuit could be connected. Here AND gate could be connected, anything could be connected. So from where this CL is coming? The CL is coming from the input capacitance of the next stage. So this capacitance, input capacitance, will depend on that W by L ratio of this stage. But the energy that is dissipated, by this CMOS is CVDD square. This energy is not depending CVDD square, or you can say CLVDD square. Here I should write CLVDD square. CLVDD square. So this CLVDD square is not depending on design parameter of this one, but it is depending on the design parameter of the next stage. Why so? Because this energy is depending on CL, and this CL is depending on design parameter of this one. Are you getting this point? This load capacitance depends on that. What is this load capacitance? input capacitance, or you can say gate to source capacitance of the next stage. Gate to source capacitance of the next stage. So that will depend on the W by L ratio, or you can say design parameters. So that will depend on the design parameters. So what is the energy dissipated by this particular CMOS? That is CL VDD square. That is CL VDD square, and this CL is depending on the design parameter of the next inverter. So yes, the energy dissipated by a CMOS will depend on the design parameters, but design parameter of the next stage. Okay. Now someone will have a doubt, sir, that sir, this CL that you are telling, this CL is coming from the input capacitance of our next stage. That is fine, but this will come from these capacitors as well, no? Like this is having CGD capacitor here, this is having CGD capacitors here. So if you apply Miller's, so this stage will also have some parasitic cap. So in this CL, only the next stage capacitor is not there. The capacitor of this stage is also there. In this CL, the capacitor of this stage is also there. So this CL is combination of the next stage capacitor, input capacitor of next stage, and capacitors of this stage as well, this particular stage. So if you see on a top level, if you see there, so you will find that this CL is depending on the design parameter of this one as well, because this CGD and all these capacitor that we call parasitic cap, that would depend on the design parameter of this particular CMOS, right? So someone will have this doubt that, sir, the CL is depending on these cap as well. So yes, the CL is depending on these cap as well, and your dynamic power somewhere depends on your design parameter. Are you getting this point, what I am saying? If I change the W by L of this, then this CGD CL will change, and if this CGD CL will change, so then this CL will also change. It will change, and if this CL changes, then your dynamic power will also change. But you would see in simulation you can run, if you change the W by L ratio, then you would see that there is very less change in power dissipation. Okay, there will be very less change. The CL is depending on these caps, but not that much. The major part of the CL is coming from the next stage. Okay, so this will not affect much. What you do, you connect two CMOS in series, okay, and then you calculate the power dissipation. Then you change the W by L ratio and see if there is any change in the power dissipation or not. So there will be very minute change. Why is that so? Because this CL is not depending majorly on these W by L ratio. This CL is depending majorly on the next stage of W by L ratio. So if you change the W by L ratio of this stage, then there will be change in power dissipation. Based on that, this CL can change. Are you getting this point? This point is very confusing sometimes, but I hope this is clear now. So till now what we have studied, let's summarize it. So we started from this simple question that we got to know that this is driving CL VDD square, this will have half CL VDD square, this will have half CL VDD square. Then we are going to start studying about dynamic power, but till now we are not studying about power, we have already studied about energy. So from 1 to 0 if I am going, so this will be turning on, this will be driving, initially it was 0, this will take VDD voltage. So that means from here C VDD square is delivered, this is having half C VDD square, so across the resistor half C VDD square would have been dissipated, right? So my NMOS, so my PMOS is having half CVDD square energy dissipated. Same goes for this one, this was having half CVDD square, so this was already storing half CVDD square energy, so that is completely dissipated across the resistor. So energy dissipated across the NMOS is half CVDD square. So in a cycle 0 to 1, 1 to 0, the complete energy that is dissipated across the CMOS, that means across PMOS and NMOS, that is CL VDD square. And that is not depending on the design parameter, but it will depend on the design parameter of the next stage. That next stage could be another inverter. If the next stage is another inverter, then certainly it will depend on the design parameter of that, because WIL will change this CL load. Okay, so that is the conclusion. And someone will have the doubt, sir, because if this CL will depend on the parasitic cap of this one as well. If it is depending on the parasitic cap of this one, then CL will change. If I change the WIL ratio, then CL will change. If CL changes, then then this energy will also change. But yeah, it will change, but CL will change very minute. There will be very minute change in CL. So eventually it is not depending that much on the design parameter of that particular CMOS where you are calculating your dynamic power. So till now everything is crystal clear, right? Now let's proceed. Now I'm gonna find my power. Okay, now let's see a combination circuit. Let's just say this combination circuit I am designing using CMOS logic. Using CMOS logic I can design this combination circuit, and to the input of this particular gate, this is my NAND gate, this is designed using CMOS. All are designed using CMOS. All are designed using CMOS. This is simple CMOS inverter only. So all are designed using CMOS. If at the input of this NAND gate I fix my input, that is 0. If I fix this input 0, so this output is also fixed. So is the output changing? Output is always 1. So when the dynamic power is coming in action, when you are changing, when you are going from 0 to 1 and 1 to 0, when there is switching from 0 to 1 and 1 to 0, at that time your dynamic power is coming in action. When it was constant here, at that time dynamic power was there? No. If my output here is constant, it is 1. So how much dynamic power it is taking? 0. And if you apply the formula, what you will say that, sir, this CMOS will take CL VDD square, and sir, this CMOS will take CL VDD square, and this CMOS will also take CL VDD square. So you will say that combined it is 3 CL VDD square, that is energy, that much energy is dissipated. But that is wrong, because output here is fixed. So you need to introduce a factor that will tell that how much time your output is changing or toggling. You can say toggle from 0 to 1 or 1 to 0. How much time it is toggling. So that is known as activity factor. So it shows the probability of a particular node that is changing from 0 to 1 or 1 to 0. Here this node is not even changing. So for this the activity factor is 0. At the steady state it is not even changing, it is fixed. So for this activity factor is 0. Okay, so this is something we define. So let me write it down. So what was the energy for every charge and discharge cycle? That total energy was CL VDD square. But now we are introducing another factor. So with that factor we need to multiply our total energy. So this is known as activity factor. Let me explain it to you in more detail. So let's just say this is my clock cycle. This is the input that I am applying. So at output as well, the same kind of oscillations you will see, right? The same kind of input, the kind of input you are applying at the output of the inverter, the same kind of output you will see. Like from 0 to 1 it is going, so from 1 to 0 it will go. So your output will also toggle in the same manner. So if I am defining the activity factor for this as 1, so tell me what will be the activity factor for this? If this is consuming half CL VDD square energy, so how much energy this will consume? Tell me how many transitions are there? This I will call one transition. From 0 to 1, 1 to 0. In 0 to 1 and 1 to 0, you total consume CL VDD square. What do I mean to say is that from 1 to 0 and 0 to 1, total you consume CL VDD square. So from 0 to 1, 1 to 0, CL VDD square, CL VDD square, CL VDD square, and CL VDD square. So eventually if I am writing it is CL VDD square, so effectively it is 4 CL VDD square. What about this? 0 to 1, 1 to 0, 0 to 1, 1 to 0. How many cycles are there? 2 only. If activity factor for this is 1, so what will be the activity factor for this? If it is consuming, if it is taking 4 CL VDD square energy, then this would be taking 2 CL VDD square energy. So that is the activity factor alpha I am multiplying. What happens is that, let's just say I am designing a chip. Not chip, I am designing any particular sequential circuit or combination circuit. I am designing a combination circuit using CMOS technology, using CMOS circuit. So when we were studying logic families, there I told you there we designed D-latch. In one of the questions we designed D-latch using what? Using CMOS. Using all the CMOS component we designed D-latch. So the same latch, or you can say now I am designing flip-flop. Using the same that same circuitry, I am designing flip-flop using CMOS technology only, or I should say using CMOS logic family. I am designing this particular D latch or D flip-flop. So there will be a clock and there will be a data. Now this data will also be fed to some inverter, and this clock can also be fed to some inverter. So output of this, let's just say this D flip flop is working in toggle mode. So output of this will toggle if this is my clock. If this is my clock, so how the output of how this output is, basically this D input is applied at the input of this inverter. So how this output will go from 0 to 1, 1 to 0, 0 to 1. So this is what I have drawn here. This is my clock. With respect to clock, if I am defining alpha equals to 1, then this alpha here will be half. So in any what do we say, if you design any sequential or combination circuit, the clock will always have your activity factor as 1. So how will a random data will have activity factor? That will be that you need to see in a clock cycle. In a clock cycle, how much transition are there? So in two clock cycle, one clock cycle and two clock cycle, there is 1 0 to 1 and 1 to 0 transition. In two clock cycle, 0 to 1 transition is there and 1 to 0 transition is there. So total it will take CL VDD square. In two clock cycle, that means I need to multiply by half CL VDD square. Are you getting this point? For this, what is the activity factor? For the next waveform, tell me the activity factor. That would be 1 by 4. So I will erase everything. So for this, my activity factor will be 1 by 4. So what will be my power? Power is the rate of change of energy with respect to clock frequency. With respect to clock, I can write rate of change of energy. Rate of change of energy with respect to clock. Okay, fine. So what will be the power? Power is actually energy by time period. So in one time period, how much energy dissipated? CL VDD square. And this is my time period. So this is the energy that is dissipated divided by T clock. So F clock. But that will only work for clock. If I need to generalize it, I need to multiply with ideality factor. Because this much energy is dissipated in one clock cycle. If I put alpha equals to half, that means in one clock cycle, half CL VDD square only I am dissipating. Because I am only going from 0 to 1. In one clock cycle, I am only going from 0 to 1. So only half CL VDD square is dissipated. So that's why I need to multiply with this ideality factor. So a lot of times we write dynamic power is CL VDD square F clock. That is wrong. If this we are writing, then we are writing only with respect to clock. So here I am not writing with respect to clock. So what is the total dynamic power of any particular CMOS circuit? Of any particular CMOS circuit, what will be the dynamic power? That would be CL VDD square into F clock into alpha. Alpha is the activity factor. So this is the expression of, this is, I can call, this is my T clock. Okay, yeah. So this is the expression of dynamic power. So this is our dynamic power. I hope this is clear to you. Let's see what we are going to see now. Now the thing is how to control this dynamic power, because we would want least power to be dissipated across the CMOS. So how do I control it? What do you think? I can decrease CL value. I can decrease the supply. I can decrease the F clock. So let's try it one by one. If I decrease CL, what do you mean by CL? The CL is coming from the next stage. So if I connect more and more, inverter here, if I connect more and more inverter here, if I connect more and more inverter, what does that mean? That more inverter are there, that means more CL will be there, right? All the CL will come in parallel across this node. CL from this node to ground, CL will be there. From this node to ground, CL will be there. From this node to ground, CL will be there. From this node to ground, CL will be there. So a lot of CL will come in action and all will be added. So CL value will increase. If I want to reduce CL, what does that mean? That I need to connect less inverters. Across the output of inverter, I need to connect less inverters. So if I am connecting less inverter, what does that mean? That I am reducing my fan out. reducing my fan out. So if I am reducing CL, that means I am reducing my fan out. So if I reduce CL, that means at the output of the inverter, you will connect less stages. But let's just say if my design requires me connecting 4 stages, so what I can do? I will have to connect 4 stages, right? So if I am reducing CL, that means I am reducing my fan out. So you will have to compensate whether you need a good fan out or whether you want your power to be reduced. So that you need to see as per your design. Okay. And second task I can do is that reduce VDD. If I reduce VDD, what will happen? What do you think? Like किससे मेरे को compensate करना पड़ेगा? What wrong will happen? Let's just say my VDD is 5 volt. Initially my VDD is 5 volt, and here I will apply V in. So if I apply V in equals to, and I am considering my VT is equals to 1 volt. VTP and VTN all are 1 volt. So if my V in is 4 volt, then this transistor will turn on. And if my V in is 3.9 volt as well, then also it will turn on. So the maximum voltage that I can apply to turn on this transistor is 4 volt. But let's just say if this reduces to 4.2 volt. If I am reducing it to 4.2 volt. So what is the maximum voltage that you can apply to turn on the transistor? 3.2 volt. So your VIH has reduced. VIH, the maximum input voltage above which you will consider input logic as 1. So that has reduced. That means your noise margin is also reducing. I am not able to get that word. That matlab ki trade off. Yeah, that means you are trading off with noise margin. If I am reducing my supply, then the applied input that I can apply to turn on that transistor, that is being reduced. That means my VIH is reduced. So if VIH is reduced, so I am doing? I am trading off with noise margin. So if I reduce the supply, then what will happen? Noise margin reduces. So effect of noise will increase. Now the third factor could be reduce F clock. So that we will see when we study leakage power. So if I reduce F clock, then my leakage power will increase. So that we are going to see if I reduce F clock. Okay. And in your design, you are never going to change VDD. Okay. You are never going to change your supply. So that is highly not recommended to change the supply. This is just one of the factors that I told, that noise margin reduces. Other factors could also be affecting that supply. If I reduce the supply, then other factors can also come in action that will make my design worse. So this is the worst idea that you can put, that I will reduce my supply. In very rarely you will change your supply. Your supply will be constant. So that you cannot change. This you can do, that you will decrease the fan out. And if you increase the F clock, if you decrease the F clock, that means if you increase the time period of the clock, then leakage power will increase. So in your design, with the clock also you do minimum of things, that you can decrease the clock frequency, but that is not recommended at all. That is also not recommended. But yeah, certainly you can go from F clock to F clock by 2. But that also you need to check in your design, because leakage power will increase. How it will increase, that we will see. Don't worry about that. When we study leakage power, at that time we will see. So that's it about our dynamic power. Now we are going to study about short circuit power. Okay. So let me see here, noise margin reduce. Okay. Yeah. So short circuit power. So till now I was taking this input, 0 to 1 it is directly going, 1 to 0 it is going, right? Now if my input is this, if my input is something like this, so for this input, I know how will my output characteristics will look like. This is my input. If my input is rising like this, ramp input, for ramp input we have seen this characteristics, say yes or no. So this is how the output will go. So before VTN, your PMOS was on and NMOS was off. If this was low, from 0 to VTN, this was off and this was on. And from here to here, PMOS was on and NMOS was, sorry, PMOS was off and NMOS was on. In between these two, in between these two, both were on. Say yes or no. So what I am saying is that from VDD to ground, I am getting a IVDD. From the supply, I am getting some current, that is IVDD. So from VDD to ground, I am getting IVDD. So that I need to see during the transition how much current I get. So in this case, your PMOS was on and NMOS was off. So at that time, there was no direct current to the ground. Say yes or no, because this was off. This was on, but this was off. So there is no direct current. That means till this point, the current was 0. There is no doubt about that. Now here both turns on. This goes to here. This was in linear. This was off. So what happens? This goes to linear, and NMOS goes to saturation. This happens here, and here both comes in saturation. And here what happens at VDD by 2 both comes in saturation. Here this goes to saturation and this goes to linear, right? This is what happens. Now, if both are on, that means they will drive some current from VDD to ground. So that current will start increasing. Tell me at what point it will become maximum? At this point. Because here both are in saturation. If both are in saturation, both can act as a current source. That means from VDD to ground, you are having a direct path. So at that time, your current is maximum. So when you are transitioning, you would see that your current increases and then it decreases. So this kind of curve you see here. If this point is your VTN, this point will be your switching threshold. I am assuming my Kn is equals to Kp, so that's why I put this as VDD by 2. But this can change as well. The switching threshold can change. I hope you know it because we have already studied it, right? So this switching threshold can change, and this is my VDD minus mode of VTP. Somewhere you can find this as this written as VDD plus VTP. So if they are writing VDD plus VTP, that means they are considering that my VTP is negative. Here I am writing VDD minus mode of VTP. So this negative sign I am compensating. Basically, if my VDD is 5 and VTP is minus 4, sorry, minus 1, VTP is minus 1, so it would be 4. And here what I am writing? VDD minus mode of VTP. So same thing we are writing. You can find somewhere plus VTP written, but there they will not write mode. They are considering VTP is negative. Okay. And after this point, what will happen? PMOS is off and NMOS is on. So again from supply to ground, you are not getting any current. So here also the current will be 0 till this VDD. So here you have reached the steady state. Then again the same cycle will repeat here as well. In this cycle as well, you will have the current again. Again this waveform will go. So here you are having a maximum current V peak I am showing. So basically then what you can do is that I am not going to write the expressions. Expressions are not important. If they are asking you what is the short circuit current, so what you will tell that, sir, if my input is rise, my input will rise, it will have a finite rise time and fall time. And then after crossing VTP, what will happen? Both transistors will turn on. If both are turning on, that means from VDD to ground, I will have a current. I will not say it is a short circuit current, but I will have a current. So because of that current, VDD into IVDD. This I am drawing the waveform of IVDD with respect to my V in voltage. So because of that VDD into IVDD, some power will be consumed. So that is known as short circuit power or switching power. And when at the switching threshold, both PMOS and NMOS will be in saturation. That means from VDD to ground, we will have a short circuit path, and at that time there will be very high power consumption. Okay, so that will be very high power consumption. In this complete scenario, this will be the most dominating one. Okay, so that much power it will take. So that is known as short circuit power. So in CMOS, how many power consumption we have studied? Dynamic power we have studied and short circuit power we have studied. These two are the major part, and in this as well, the major part is dynamic power consumption only. Okay, dynamic power consumption will be much more than this short circuit power consumption. That is this. Okay. Now we are going to see leakage power. So the leakage power occurs when you have the steady state. When you are transitioning from 0 to 1 or 1 to 0, when you are transitioning from 0 to 1 or 1 to 0, at that time what was your things occurred? When you were transitioning from 0 to 1 and 1 to 0, what all powers occurred? Dynamic power. Dynamic power. Also, this is short circuit power. So these power came in action during the transition. When it is at steady state, what do I mean by steady state is that this is my 0, this is my 1. Let's assume a capacitor here. Let's assume a capacitor. So when 0 was there, this was charged to complete 5 volt. This was completely charged to 5 volt. When 0 was there, this was charged to 5 volt. When 1 came in action, this has been completely discharged. So here you are having 0 voltage. Right? When 1 is in action. When 1 is in action, this PMOS is off. This PMOS is off. When 1 is in action, this PMOS is off. When 1 is in action, this NMOS is on. This NMOS is on. And this capacitor is charged to 0 volt. Because till this point, the capacitor would have charged to 0 volt only. You can say that if this is rising like this, then my V0 would have gone down to 0, right? So this would have been discharged already. So across the resistors, across the PMOS, how much is the voltage? 0 volt only. So how much power it is taking? 0. The power dissipated is 0. If there is a finite rise time, in this rise time only you are having dynamic power as well and short circuit power as well. But when you have reached the steady state, if I go from 1 to 0, it will make more clear to you. Okay. If I go from 1 to 0, so when I was at 1, this was completely discharged, because at 1 this NMOS was on. If this NMOS was on, then it would have completely discharged it. So when I was at 1, it was completely discharged. Now I am going to 0. That means if I am going to 0, then this PMOS will turn on. If this PMOS turns on, that means it will charge it to 5 volt. So when you reach this point, it would have been charged to 5 volt. Right? Now what will happen? The input is 0. Input is 0, that means NMOS is on. Sorry, PMOS is on. If input is 0, PMOS is on. And this is your VDD. If input is 0, PMOS is on. And this capacitor has charged to 5 volt. This was your VDD was also 5 volt. What about NMOS? NMOS is off. So this is your 5 volt, this is also 5 volt. So what is the current through this resistor? 0 amp. If this current is 0 amp, that means your static power, or here we are analyzing. Here when your input is constant, so this is known as static power, which should be 0. Static power should be 0. When input is constant, your power should be 0. But because of the leakage, there is some power. Because of the leakage, that means this NMOS will drive some power. Are you getting this point? Here this NMOS is off. In this case, when we have reached to this point, when applied input is 0, this NMOS is off. But still, because of, it could be in sub-threshold region or because of any region, there could be some diode as well. Like if you go deep into the device physics, you can analyze that basically because of the sub-threshold, you can say this NMOS will leak some current. Some current it will leak. So that is known as leakage current. Here ideally it should be 0. The power here should be 0 because current should be 0. But because of some regions that we are not looking at it, but because of some region, this will leak some current. And if it is leaking some current, that means from VDD you are having some current coming. Ideally from VDD 0 current should be coming. But if it is leaking some current, so from VDD you are having some current. And from VDD if you are having some current, that means some power would be there. So that is known as leakage power. Not important, they are not going to ask it. They can ask in CMOS, what is the static power? Static power, ideally it is 0. When you have reached here, ideally static power is 0. Now in the next, in next lecture or somewhere, we will see that when we were studying logic family, I told you we will use CMOS circuitry, not PMOS or NMOS. And there I gave you the reason that if we use PMOS or NMOS, there will be some static power. In steady state as well, some power will be consumed. But when we use CMOS, in steady state, no power is consumed. So static power is 0. Only some power will be consumed because of the leakage. So because of the leakage, NMOS can drive some current. It could be working in subthreshold region, so it would drive some current there, or if it is replaced by a diode, then also it can drive some current. So because of that, even if it is off, then some current it can drive, and because of that some power will be consumed. So that is known as leakage power. So in this region you will have leakage power. In this particular region you will have leakage power. Leakage power. Okay, we are not looking at the expression. What is the important part? Important part is they will ask what is the leakage power, what is the short circuit power, what is the dynamic power, when does they occur, what is the meaning of that, what is the formula, what is the meaning of this activity factor alpha. So these things they can ask. So that we have covered, and ideally your static power is 0. Here I am writing some current, even if it is off, it can drive some current, and then because of that leakage power will come. Ideally static power is 0. This is known as static power when input has been stable. When input has been stable, so how much power it is consuming. So ideally static power is equals to 0 amp. Okay, well and good, right? Now let's see some small points. So in our digital electronics course, when we were studying ring oscillator, so what did I tell you? That for a CMOS, for any inverter, if you connect back the output to the input, then what will happen? It will be working as a ring oscillator 0 1 0 1 0 1, and it will be generating the clock. But that is wrong. Okay, for clock generation you need at least 3 inverters. Just to show it, actually to be very honest, I thought that this will work as a clock generator, but then I posted it on LinkedIn, and some of my senior commented that you need at least 3 inverters. Then I thought of it, then I got to know, yes, I need at least 3 inverters. If you just connect one inverter and you take the output and feed it back to the input, it will not work as a clock generator. There will be some issues. What issues will be there? Let's check that out. So for clock generation, at least 3 inverters should be there. If you just take an inverter and connect back the output back to the input, it will not work as a clock generation. Okay, we have also drawn the output as well, that I showed that it will be 0 1 0 1. This will be the clock I will be getting, but no, that is wrong. Why that is wrong? Let's check that out. So this is our CMOS inverter. At output I can assume some load is there, and this is fed back as the input. This output V0 is connected back to the input, right? What will happen? Initially this capacitor is uncharged, so this 0 will go here, this 0 will go here. Now if this 0 goes here, this will be turning on. If this turns on, then it will charge the capacitor. So now capacitor voltage will start going up from 0 to 1 volt. Understand this? Did you understand this point? This was 0, this 0 went here, this PMOS turns on, this NMOS is off. Now it start going up. I am assuming Vt is 1 volt and this VDD is 5 volt. So it is going from 0 to 5 volt. Just as it has reached 1 volt. So if this potential is going up, that means this potential is also going up. That means this potential is also going up. So at 1 volt, when your output is 1 volt, at 1 volt, if your output is 1 volt, so this is also 1 volt and this is also 1 volt. This is on, 5 minus 1, you are having good margin. This is also on, and this also turns on. And this turns on in saturation region. This is on, and this is already on, and this also turns on. If this turns on, then what it will say? That bro, you discharge now. And what this will say? Bro, you charge now. So the latch-up condition will occur. We are not sure whether your output will be at +1, it will charge or discharge. Secondly, if both are turning on, if both turns on, then static power, if both are turning on, in the region when it both turns on, then this short circuit power also come in action. So there will be high power consumption. And let's just say if it is charges to 2.5 volt, then both will be in saturation region. And when both are in saturation region, it will create more issue for you, because more power consumption will be there. So there, if you see this configuration, then you would see that output is unstable, and also there is more power consumption. Output is unstable, not I should say output is unpredictable. You will have an unpredictable output, and there will be high power consumption, because both of the transistor PMOS and NMOS will be turning on. Because the output that you are having, that is directly connected to the input of both of the transistor. So output is driving your biasing. So this is known as self-bias circuit. This is self-bias circuit. What do you mean by that? From 5 volt only you charge the capacitor, and that charge that you are having, that is fed back to the input. So that is working as a biasing. What do you mean by biasing? To turn on the transistor, whatever the voltage we apply. So that is known as the biasing. So whatever the voltage that you are having at the output, the same voltage is being fed at the input of the transistors. So because of that, this voltage is going up, this transistor is turning on, and if it is turning on, both are turning on, then there will be high short circuit power consumption. So if someone will ask you, if you connect the output and to the input, what will happen? The power consumption will increase. High power consumption will be there, and unpredictable output will be there. High power consumption and unpredictable output. So that was an error from my side, which I have modified here, that when I connected this, that was wrong. What you would say? For clock generation, you need at least 3 inverters. So that was a good point. From now onwards, I will not do this error. So I have modified my notes now. So this is the thing you need to take care. Also, you must have thought that it would go from 0 to 1, 1 to 0, but we need at least 3 inverters there. What else we can study? Yeah, this transient response we can see. Okay. So if I say this applied input is there, if this is the applied input, then how will your output look like? Then you will say that, sir, it should go like this, right? Or you can say that, sir, somewhat like this, somewhat like this. So somewhat like this, a bit of curvature would be there. But when you do the simulation, like those M.tech guys must have done the simulation, at least this simulation they must have done. What they would see is that if you give the input waveform with a finite rise time and fall time, what you would see is that it will go like this. And then when it rises up, it will go down a bit, and then it will be rising up. This is what you must have observed. So why this is happening? So just a small intuition I will give you. What happens is that here there will be some CGD cap now. And if you remember our analog electronics course, if we connect a cap in between, that will result in a 0. This will result in a 0, right? This capacitor will result in a 0. If you apply Miller's theorem, you would see that, sir, this is not resulting in a 0. But when I told you that if this is driving some current, so 1 0 will be there. And because of 0, this shoot is there. It was expected to go like this. But since there are CGD cap available, so because of them, 1 0 will be there. 0, what do I mean by 0? Pole 0 I am talking about, pole 0. That 0 I am talking about, okay? So if because of that 0, this will be a, you will see a bit shoot, then downward you see a shoot, and then it will go. Okay? So because of that, that is the reason. This is what I feel. I saw this waveform in Janaki Raman sir course. Okay, Professor Janaki Raman sir course. I showed this waveform, and there I couldn't understand the reason. There he did not give the reasoning, I guess. But what I could see is that there he told that there are CGD cap. So because of that it is happening. So what I could see is that that will result in a pole. If that is, if they are resulting in a pole, then certainly there will be a overshoot. So that could be the reason. Why this will be overshoot if there is a pole? You must have studied in the control systems, right? In control theory, you must have studied if your transfer function is of s upon s plus a, or you can say s upon s square plus 2as plus omega n square, then this overshoot will come. So because of that, this overshoot is coming. This is what I feel. I don't have that much deep knowledge about device physics that I accept. If you want to study more in depth about all these things, you can go to Janaki Raman sir course. You can study there. Okay, he is a great teacher, great teacher. Okay, also there is a course by IIT Roorkee as well. Also there is a course by IIT Delhi as well on CMOS circuit design. So that you can study if you want to go in depth. I am not covering that much in depth. First thing is that I myself don't have that much of knowledge, and secondly, as per like for the interview purpose or at UGPG level, you might not be able to study these much of things. at least at UG level. At PG level, you should study. You should at least do the course by Janaki Raman sir course, that digital IC design course that you should be doing, at least at PG level. But UG level, sometimes what happens is that we don't focus much on that, but getting the interview goals and getting into the industry, that is also a very important part, right? So for that purpose, you might not be doing that particular course because you need to do a lot of things as well, or a lot of extra things as well. And if you keep on doing the courses, then you might not be able to get a good placement. But that is also an important part, that you need to get a placement as well. Along with that, you need to gain your knowledge as well. So once you are done with all your tasks, once you are done with your college assignments and everything, then I made a video as well that which courses you need to do. So once you are done with those tasks, then you can do those courses that will enhance your knowledge, and these things will be highly used in the industry, right? So yeah, so this is the reason that I am thinking that this overshoot will be there and this undershoot will be there and this response will be there. Mostly what they can ask is that in the interview they can directly ask, if this input waveform is given, what will be your output response? So you wouldn't say that, sir, it will go like this. Okay, what do I mean to say? Sir, this will go like this. No, this will not go like this. There will be a overshoot because there are CGD connected, and that will result in a 0. And if that is resulting in a 0, there will be overshoot, right? We can see more things. We can see noise margin as well. So I will deal noise margin as well. In this video only I will connect it. So I will make the content and then we will see noise margin. And here, did you understand the point about the leakage power? If this width is more, what did I tell here? That if you increase f clock, if I increase f clock, sorry, if I decrease f clock, I need to decrease this dynamic power consumption. If I decrease f clock, then what will happen? T clock will increase. T clock will increase, that means this area will increase. This one will be there for a longer time. If this one is increasing, what does that mean? The leakage power will increase. Because leakage power come in action when it comes in action, when this is 1, so leakage power will increase. Okay, we can see the noise margin as well now. So we will see that noise margin, and with that it should be completed. Okay, so we will see the noise margin in this video only. I will make the content and will add it up.